First of all, you said that I was going to talk about the QIX engine. We are internally in Qlik told that we're not allowed to use that anymore. It's not called the QIX engine, it's called the Qlik engine. And in fact, internally in R&D, QIX means the protocol between the client and the server. So when the marketing clown decided to call it the QIX engine, we were, why? Shouldn't do it that way. And now they returned, and now we're called the Qlik engine again. So anyway, I'm going to talk about the Qlik engine, how it works internally, and what makes the magic. Because to most people, Qlik View and Qlik Sense are tools that show you information, but not very many people think about what happens behind the curtains. So that's what I'm going to talk about a little. It's going to be very technical in some periods, so bear with me. Techies love it, and you others, you can bear with me for a while because you will see the business advantages of it also. So, those of you who saw me this morning, you know who I am. I'm called Hick internally and externally on community also. I've been with the company quite a while, and I've always worked in the borderland between development and sales. I've been product manager, meaning picking up customer needs when you are at the customer site and communicating that back to the R&D, the developers. And I've been working with the other side, also bringing information from R&D out to the field as a technical product advocate. Right now I work with product design, meaning deciding what we should have in the next versions. And I work more specifically with advanced features that we want in Qlik Sense, but they are not there yet, but they are in Qlik View. We see today that there are many customers that don't want to upgrade to Qlik Sense because there are things you cannot do with Qlik Sense that you still can do in Qlik View. There are things like actions and triggers, accumulations, trend lines. There are a number of things, number of features that we want in Qlik Sense, and I am working on defining how these should work and pushing the developers to introduce them. That's my job. So if you have ideas about what you want, mail me. My mail address is obviously hick@qlik.com. So, the Qlik engine, what is it? That's what we're going to talk about. We're going to talk about why and how the engine is different from other tools on the market. We're going to talk a little about something we call symbol tables and bit stuff indices. We're going to talk about the logical inference versus calculations. And we're going to talk a little about what aggregations are and how they are performed inside the engine. So first of all, what is the engine? Very simply, it's the back end of the product. So whether you have a desktop product where everything is packaged into one thing, and with desktop I mean Qlik View desktop or Qlik Sense desktop or the iOS client, they all contain the engine. So inside such a product you have both the UI part and the backend part. Or you work with Qlik Sense or Qlik View on a server client situation. Then you have a web client and you have a server. And in both cases, the Qlik engine is the back end, the blue part here on the screen. And it has 7 different components. And when I say components, don't think of it as modules. It's more like functional components. What does it do? What problem does it solve? If you have external data, you load it with a data load engine, basically the script interpreter. And once you've done that, you can save it in the database, the internal database. And once you've saved it and want to open it again, then the authorization engine kicks in. And that means deciding, are you allowed to open this data or not? And if you're allowed, what records are you allowed to see? Then we have the logical inference engine, which is what happens when you click. That's the green, white, gray. And then you have the calculation engine. That's the number crunching part. So whenever you have a bar chart that shows sum of sales or something, then the calculation engine has done its work. And then there are other components like rendering engine. When you have the result, you want to draw it on the screen also. And this is done differently in Qlik View and Qlik Sense. In Qlik View, we very often produce an image on the server and then we send the image to the client, whereas in Qlik Sense, we always send the data to the client and have client-side rendering. And then there are some export features, but I'm not going to touch those at all. In fact, I'm going to talk mostly about the logical inference, the internal database, and the calculation engine. So, in order to continue, we have to talk about symbol tables and bit stuff indices. And to understand what those are, we can look at a case if you load data. Let's say that you have a small table like the one up to the left here. You have 5 products. Each product has a list price, and each product has a flag saying, do we have it in stock or not? It's a very small table, 5 rows, 3 columns. So what happens then is that the engine breaks up these 3 columns and stores them in symbol tables. 1 table per column, 1 table per field. And note that the first column, the product, has 5 distinct values. Well, then the symbol table gets 5 rows. The list price has only 4 distinct values. Well, then the symbol table has 4 rows. And the flag only has yes or no, 2 rows. So we store a minimal amount of information in the symbol table. But the symbol table also has an address built in here. That's the bit stuff index. And you can see that in order to address 5 rows, we need 3 bits. And in order to address 4 rows, we only need 2 bits. And in order to address 2 rows, we only need 1 bit. Now note that we use bits here. We don't use bytes. Any other product would use a byte to address, because that's a lot easier. But we use bits, which means that it takes much, much less space in memory. Okay, now we have created the symbol table. Now we also create the data table, which basically is a copy of the input table. If the input has 5 rows and 3 columns, then the data table also has 5 rows, 3 columns. But in the data table, we of course use the bit stuff indices. So here we have an extremely compact data model, but we haven't lost any information at all so far. Data tables and symbol tables. And that's the main part of the internal database in the engine. Now, what does it mean? What are the implications of having it like this? Well, of course, if you have many field values, then the symbol tables will get very, very long. And not only will it get long, the indices will get symbol tables. If you have many distinct values, then of course the symbol table becomes very long, and also the index becomes very long. So it takes a lot of place in memory. So then you should ask yourself, do I need this many distinct values, or is there a smart way to reduce the number of distinct values? You could, for instance, have a timestamp. Let's say that you have input data, 10 million records, and you have a timestamp in it that goes down to milliseconds. How many timestamps do you have? 10 million, most likely. There may be 1 or 2 duplicates, but very unlikely. So you have 10 million records in your symbol table. Do you need that? Do you need milliseconds? Well, sometimes you do, but usually you don't. So a way to optimize the engine is already at script time that you do something smart with this. You could, for instance, use this function here. I use a floor function which rounds it off to the closest value, and it rounds it off to the closest minute. And then I format it using the time function, and I format it as hours and minutes. Now, if I do it that way, then I have 1,440 values per day. That's a lot better than 10 million, I can assure you. So that will shrink the symbol table in length and shrink the bit stuff index in size. So if you do that, then the symbol table takes a lot less place. There's another common case, and that is that you have very, very long field values. It could be, for instance, that you need to concatenate different keys in your data and make a link table or something. Well, then you should ask yourself, do you ever want to show this field? And because if you don't, then you should wrap it in the auto number. Because the auto number will just skip the clear text part of the field and just keep the number. So still, no information is lost really. It will work just as before, but you can't show the clear text value. In fact, the engine is even smarter than that. When it sees the auto number, it skips the symbol table all completely. Because the bit stuff index, that is the same as the number. So you don't need to show the number anywhere. So this is an extremely efficient way of reducing the size of the symbol tables. So 2 small tips on how to reduce the size of the symbol tables. Okay, now we have built the symbol tables. Now we start clicking to color code the information on the screen. And that we call colors and state vectors. You should think of it like this. Every field value has 2 flags internally associated with it. This is just internal bookkeeping, but it's important to understand that we have it and why we have it. There are 2 flags. Each field value can be selected or not selected, and each field value can be possible or not possible. Very straightforward. But now comes the tricky part. These 2 flags are independent of each other. Now this is not what you would think naively. Of course you think that if it's selected then it's possible. But no. It's not that simple. So when we show the green, white, gray, we have reduced something complex to something simple, understandable for the user. But behind the curtain, it's quite complex. It is like this. The selected or not selected, that's the two rows. And whether it's possible or not possible, that's the 2 columns. And then you can see that there are 4 possible combinations. There is one combination here that looks strange, and that is the selected excluded. Does that really exist? Oh yes, it does. Think of it this way. You still have your 5 products, and now I say, okay, give me the expensive products. I want those with list price 20 or 30. And in addition, I want the ones that are in stock. So now you can see that just by clicking those 2 clicks, I have selected the bike helmets. Yes, right. Do we have any selected excluded here? Yes, we do. You can see here that the 30 is in fact selected. Otherwise it wouldn't be here in the current selections box. And it's gray, so it's excluded. So with this I just want to show that we need these 2 flags to keep track of whether things are selected or not. And there are in fact even more flags, as you will see in a second. But those 2 are the 2 important ones. Okay, green, white, gray. And in Qlik View, you cannot see that this 30 is selected excluded unless you look over here. In Qlik Sense, it's smarter. Because in Qlik Sense, you can see that there are a number of gray things up here, and there is in fact one gray that has a small tick mark on the side. That is the selected excluded. So here you can right away see whether some things are selected excluded. So we use the same color scheme in Qlik Sense, and you can also see that there is a 5th possibility here. And that is the alternative. We have that in Qlik View too, but it's by default off. You have to turn it on. And we're not going to go into the alternatives very much, but that implies that, well, there is not just 2 flags, there is a 3rd one to keep track of whether the value is an alternative or not. But never mind that, the 2 main flags are the ones we're going to touch. So, green, white, gray, and light gray, and so on. So, every time you click, the logical inference goes through the data and decides, is a field value possible or not possible? And then color codes all the field values in all the list boxes for you. And we call this logical inference. And this is what you saw this morning also in the old Qlik View version 1 that only had logical inference. Green, white, gray. And then we store the result of the logical inference in something that is called state vectors. And you can see here that for the symbol table for the products, 5 rows, we have a symbol table that has 5 rows. And, sorry, we have a state vector that has 5 rows. For the list price, 4 rows. For the flag, whether it's in stock, we just have 2 rows. So you can see that the state vectors, they are very similar to the symbol table, and we have the same number of rows. And in addition, we also have a state vector for the data table. Now, if you and I log on to the same app on a server, then of course, the symbol tables will not be duplicated. We will use the same symbol tables. But I have my set of state vectors, and you have your set of state vectors. So this way you have at least one state vector, one set of state vectors per user, but you only have one symbol table per field and app. So in this case, we have the selection stored in the selection state vector and the possible values in the possible state vector. And we have it for all the symbol table and for the data table. Now, for the data table, that's interesting because when we later talk about calculations, then it's quite obvious that we should only calculate on the numbers that have a 1 over here. So this becomes a mask for all the aggregations. We just pick out the records that have a 1 in the state vector. Okay, I said that each user has one set of state vectors. But you know also that you can have alternate states in both Qlik View and Qlik Sense now, which means that I, as a user, I can have several sets of state vectors. And it's even worse than that. Each set expression is a set of state vectors also. So I suddenly have a bunch of state vectors, and depending on how I write my formula, the Qlik engine will know which state vector to use. So if I use $, or no set expression at all, then I will use the standard state vectors. And if I use a set expression like this one, where I demand that products should be either boots or cap, then I use the additional state vectors, not the standard ones. So then it looks like this. I still have my product table, I still have my state vector from my selection, but in addition I have state vectors for the set analysis. And I didn't say this before, but of course, just as the symbol tables have bit stuffed indices over here, the state vectors, of course, have how many bits? 1. Compact as possible. So, set analysis is just like a selection. Nothing else. So the state vectors, that's the third component of the internal database. And the fourth component is, of course, a cache, because we use a cache for almost everything, which means that if you and I again have logged on to the same app, and we have identical data, and I have made a selection already, then you will use my cache, because it's not my cache. It's a common cache. And it's even worse than that. It could be that you have a different app than I have, a different file, but it's still the same data. It still reuses the cache because we have an electronic fingerprint on all the cache entries. We will recognize the data and the selection and everything that's needed to pick it out. So that's why it's sometimes difficult to look in the memory and see how much memory does one app use. Well, the cache takes 90%, and we don't know whether that part of the cache belongs to that app or that app. We can't tell. So the cache is common for the entire server. Now, let's go into the logical inference and calculations. First of all, when you make a click, that's when the logical inference kicks in, and we evaluate all the field values and calculate whether they should be green, white, or gray. And you should think of it this way, that I click on a field in a table, and then we evaluate all the records in that table. And when that is done, then the evaluation propagates to the other tables. So it looks at the keys, what possible values do I have on the key, and then uses that for the next table. It becomes like a selection in the next table, in fact. And that's the first thing that happens every time you click. And I would say that that is a small part of the response times, typically 5 to 10%. The other 95%, that is the calculation of the other objects. So the logical inference is the first step, and then you calculate all your charts. And here you have the calculation engine working. Now that the calculation engine knows what records to use, because that is found in the state vector, it aggregates over all the records in the data and does something smart. And to the engine, it doesn't matter whether you have a table or a bar chart or whatever you have. It's all the same. It's a chart or a cube or whatever you want to call it. And these cubes, they are transient hypercubes, meaning that they use memory when they're calculated, and then they return all the memory to the Qlik engine. It doesn't store it, persist it. The persisted selection, the persisted values of the data, that is in the data model. In hypercubes, that means that you have dimensions and measures. We'll come back to what that means later on. But basically, the advantage here is that you can have as many hypercubes as you want. And you can click in any one of them, and they communicate with each other. So if I click in a pie chart up there, the pie chart will send a message down to the data model and the logical inference, evaluate again, and then the other charts subscribe to changes in the data model and get the result up again. And this is in stark contrast with how BI tools worked 20 years ago, where you could set up a Cognos cube and you only have one cube. And since you didn't have several cubes, you had to put all the fields in there, and suddenly you had a cube with 16 dimensions that never answered because it took 2 days to calculate it. Whereas here we produce the cubes on demand, and we have the same limitation. If you put 16 dimensions into one cube in the Qlik engine, you'll have problems. But you rarely want to do that. You don't need to, because since you can make many different charts, you can choose the 1, 2, 3, maybe 4 dimensions that you need, and that's it. So you click in a pivot table, and you get the answer in a bar chart. Perfectly possible. So, logical inference and calculation engine. If you look at multi-threading, then it looks like this. You click over here, and the evaluation in the logical inference is spread on different threads, on different cores in the hardware. And you can see here that the first table is probably single-threaded when that evaluates, but then it can propagate in 3 different threads to the other parts of the data model. And of course we do that. We don't always do it. It depends on how much data we have, because we have realized that there's an overhead with multi-threading. So we have an algorithm that determines, is it worthwhile? If it's a lot of data, then it is worthwhile. If it's little data, then no, don't bother. So anyway, multi-threaded in the logical inference, and then next step, all the objects are calculated. And the first step in the calculation is to determine, okay, what combinations do I have here? What rows should I really show in this pivot table? And that is, in fact, a single-threaded process. You can see that. It's just 1 thread per object, not more. But once that is done, we can take 1 object and multi-thread the calculation itself. So if you have a pivot table with sum of sales, then it takes a small time to calculate what records should I have in this pivot table. But when I then make the aggregation over 10 million rows, then that part is in fact multi-threaded. Then we partition the source data and calculate in different threads. So logical inference and calculation engine, and the middle part is single-threaded. And it's a possible bottleneck. Now, to understand what part is single-threaded, I have made a small example. Think of it like this. If we have 2 tables, transactions and products, and they are linked through a key, this is a very small data set, so we can all calculate this in our head. If I ask you, what is the sum of quantity? Sorry? 10. Now, how do you know that? What's the algorithm you use to calculate that? It's so obvious you don't need to say it. But the thing is that you look at the field name, quantity, and then you look up there, where is quantity? And by that you have determined what table to make the aggregation in. Now compare that with SQL. In SQL you have to tell specifically where should I do the calculation, in what table can I find this? Otherwise you have to have a from clause, otherwise it doesn't work. Here you don't need to say that. Next question, counter product. 2, exactly, it's just 2. Over here. Anyone?
42.
Louder.
42.
Perfect. The answer is 42, as always. Why is it 42? Well, obviously, you have to look at quantity over here and list price over here, and then you have to make something smart. What happens in the background here is that you calculate the number in a temporary table that looks like this. The temporary table is produced by joining the two tables up there. And you did that in your head on the fly in 3 seconds. Good. You have the quantity here, you have the list price there, and then you create an additional column with quantity times list price and calculate that, and it is 42. Now you start getting where the single-threaded process is. Making this join in the background is single-threaded. So don't do this if you have a lot of data. To summarize, the Qlik engine determines which source table to use. If it's quantity, well, then it's a table with quantity. If it's list price, then it's a table with list price. And if you have fields from 2 different tables, then you have to make a temporary table, a join, and that takes time. So don't have fields from 2 different tables inside your aggregation function, because that takes time. You can try it, and you will see that if you have smaller sets of data, like a couple of thousand rows or 50,000 or 100,000 rows, you probably won't notice, because it's so quick anyway. But if you have 10 million rows, you will start noticing. So if the fields from different source tables are used inside the same aggregation, that's when you could have a problem. So, some implications of the calculation engine. First of all, don't use fields from different tables in the same aggregation, because that uses more RAM and more CPU. So for performance reasons, you may consider moving one field into the transaction table already at the script time. And if you look again at this model, then obviously the list price could just as well be in the transaction table. It's an extra column. It will take a little more RAM when you load it, but it will perform much, much, much better. Move it to the correct table, and when you move it, you should probably use apply map. Don't make the join, because I've seen so many times when people join to a table because it's a one-to-one relationship, no problem. And then they're wrong. It isn't a one-to-one relationship. And then you get duplicate records, meaning the same dollar is counted twice. And then the controller comes back to me and says, well, the Qlik view counts wrong. And I say, sorry, Qlik view does not count wrong. And then we analyze it and we find the problem and we fix it. Joins very often lead to duplicate records. Don't use joins in the script if you can avoid it. Apply map is a very good thing. Apply map is just a lookup function. And it just puts one single value into a table when you use it. So you know that you cannot have duplicate records. There is also a risk of incorrect calculations. Again, if you have fields from different tables, that means a join. And like I said, a join could cause duplicate records. And I'll give you this example. if you have an if function inside your sum, here you say sum of if order month equals 5, May, then invoice amount. So you want to sum the invoice amount, but only if the order was placed in May. That's a piece of cake, right? No. Of the simple reason that in advanced ERP systems, you have a many-to-many relationship between orders and invoices. You can split one order on multiple invoices. So you can, in fact, get duplicate records here. How should you do it? Set analysis, yay! Set analysis doesn't have this problem. Set analysis makes it like a selection, and the aggregation will only consider the invoice amount when you do it. So yes, set analysis is the way to go. Now, set analysis has a small overhead. So it takes a little longer time. But if it's a very small amount of data, then you may notice that it's slower. But if it's 1 million records or more, then you will not notice it. Then it'll be faster even. But set analysis is better because it returns the correct answer. So, summary when you compare logical inference and calculations. First of all, the logical inference is about finding possible values. It's about creating the state vectors. It's about coloring everything green, white, gray. And there's no number crunching in the logical inference. And in addition, it's also evaluate the set expressions. A set expression is like a selection. Whereas calculations, that is create hypercubes with dimensions and measures, aggregate multiple field values into one value, and lots and lots and lots of number crunching. So I mentioned dimensions and measures a number of times, and probably most of you already know exactly what it is, but I've seen people being confused by it, so I'm going to go through it anyway and just point out the most obvious things. First of all, an example, a bar chart. If you have a bar chart where you show the sum of sales per month, then obviously month is dimension, and the number, the height of the bar, is the measure. If you look at it more mathematically, you can see that, well, we have 12 months, and then we have 12 bars. So the number of field values in the dimension determines how many bars or slices or rows you get. The dimension is like a for next loop. Loop over the possible values, and for each value, calculate the measure. So the dimension always looks at the number of distinct values. And you have to make one aggregation per dimensional value. If you know SQL, it will look like this. You have a select statement, and you have a group by clause. Well, the group by clause is the dimensions. And sum of sales, sum of quantity, those are the measures. If you have more than one dimension, then you must think of it like a matrix or even a cube. And that's the reason why we call it cubes, because you can visualize everything like this. Here you have 12 months, a number of customers, and a number of products, and for each combination of the three, you want to calculate the number. It's a cube. And to the engine, all charts are equal. The engine doesn't care whether you display it as a bar chart, a line chart. To the engine, everything is a table that looks like this. 12 rows, each row has a number, and you have a total in addition. So, to summarize, cubes. All charts, KPI objects, and text boxes, they are cubes. And cubes have dimensions and measures. The dimensions determine how many bars you get, and the measure calculates something, a number usually, and it's always an aggregation. A cube can have 0, 1, or several dimensions, and a cube can have 0, 1, or several measures. Now, the last two bullets may be confusing, so I'm going to give you a couple of examples here. First of all, a standard cube could be visualized like this. Here we have a scatter chart, we have our 5 products, and each product has a sales amount and a quantity. It's a scatter plot. It's a one-dimensional scatter plot because you only have one dimension. And you can just as well visualize this scatter plot as a bar chart or as a table. Doesn't matter. It's the same thing for the engine, same numbers. Now, a two-dimensional chart could look like this. This is a Qlik grid chart. Here you have two dimensions. You have 5 countries and 5 products. So you have potentially 25 combinations of the two. And for each combination, you calculate the number. And you can see that, well, in Denmark, they haven't bought any shorts or any shoes. So you only have 23 bullets. But the number of possible bullets is 25. And you can display, we can visualize the same data in a number of ways, either table or bar chart. And here you can see that a bar chart with 2 dimensions, 1 measure, looks pretty much like a bar chart with 1 dimension, 2 measures. So it could be confusing. Keep track of how many dimensions you have. And now the 0-dimensional cubes. Well, a KPI object is a 0-dimensional cube. It's just a measure, no dimensions whatsoever. So what happens when you click in it? Nothing, unless you have defined something in Qlik View. Because when you click in a chart, the engine picks up the click and makes a selection in the dimension. But here we don't have a dimension, so therefore nothing happens. 0-dimensional chart, and you can display it like this or like this. In Qlik View, you can in fact have a dimensionless bar chart. You can see here sales and quantity, and you can see the units on the right side and the sales on the left side, and no dimension. It's a perfectly valid visualization. And you can show it as a table too. So, aggregation, let's go over there. Aggregations, that's a word we use all the time, and again, I think most of you know what it is, but I'm going to explain it anyway. It is just a function that can collapse many records into one record. So typically the sum is an aggregation. Then you sum all the numbers. But it doesn't have to be the sum. It could be the count. Count how many records. Or it could be the min or the max. Find the extreme values. It could be the mode, which is find the most common value. Or even the only, which is a nasty function because it returns the value if there's only one value, and otherwise it returns null. We use it a lot behind the curtain. So anyway, the idea here is to represent many records with one number, or even one value. It could be a string also. So it's not a filter. It's the same data, same scope, just different granularity. And there are a number of functions in the Qlik engine. And anyone that has written script or expressions know that there is plenty of them. And when you look at the functions, you should realize that there are different classes of functions. Most of them are scalar functions, meaning that you have a one-to-one relationship between input and output. There's one value in, one value out. Whereas the aggregation functions, here you have a number of values in, and it spits out one value. And there is, in fact, a class of function that returns an array, like agg or value list, value loop. Now, I'm saying this because if you write a proper expression, you always have to have one level of aggregation function. And then you can put the other functions outside or inside, doesn't matter. But you need at least one level of aggregation function. Otherwise, it will be an expression that could be misunderstood. So, summary. All calculations are aggregations. All calculations are aggregations. You cannot write a calculation in Qlik View or Qlik Sense without the calculation engine trying to aggregate something. They are made in cubes, and an aggregation is just another word for a measure. For the engine, it doesn't matter how you use the aggregation. You can use it to color the bar just as well as drawing the height of the bar. So don't think of measures just as the height of the bar. It could also be anything really, from an engine perspective at least. Maybe not when you talk to the customer, but that's a different thing. All field references need to be wrapped in an aggregation function, and if not, then the only function will be used, and that's not what you want, I can assure you. And just as well, the aggr function also needs to be wrapped in an aggregation function, otherwise the only function will be used. And I will give you a couple of examples here. First of all, let's go through a bar chart here. I said that all aggregations are measures, and all calculations are measures. So think of it like this. A bar chart has the height of the bars, that's the first measure, but then you can indeed also have colors on bars and calculate that with a formula. That's also an aggregation. If sum of sales less than sum of budget, then red. Obvious. That's what customers very often want. You can also sort according to a number. Is that an aggregation? Of course it is. And if you don't write an aggregation function there, you will be in trouble. Labels. You can put a label on top, up here. That's also an aggregation. So always think about what aggregation function to use. You can choose not to use it, but think about it, because then you're in control and will understand what you do. You can have show conditions, reference lines, axis min-max. They're all numbers that are calculated, hence aggregations. But you can see here that the bar chart has one dimension, whereas these, or the bottom one, has 0 dimensions. That's the same for the entire chart. So they can have different dimensionality inside the same chart. If you have made expression searches like this, then these are also cubes that are evaluated in the background. In this case, I mark a list box called country, and I write sum of sales should be greater than 100,000. Well, of course, then I demand, give me the countries that have sum of sales greater than 100,000. Perfectly valid, and what happens then, that in the background, the engine will create a cube that looks roughly like this. It will list all the countries, and then calculate that expression, and get true for some countries, false for others. And when you hit return, of course, you will select the ones that have true. That's also a cube. And here we go now with the only function. If you don't wrap it in an aggregation function, then if you write country, then that will be interpreted as only country. Meaning, if there are several countries possible, it will be null. And as I said, that's probably not what you want. Same thing with month of order date. If you have multiple order dates, then potentially it will be null. And a non-aggregated field reference will sometimes result in an incorrect calculation. So therefore you should wrap it in min-max, average, or min-string, or something like that. I will give you an example of when it can in a while. But first let's take next slide here. If you have used the aggr function, then you should think of it like this, that the aggr is a function that creates an intermediate cube. You want to look at this cube over here. So if you want a table with dimension, year, then you have that here, and the measure should be max aggr sum of sales, meaning, well, I want the largest order within each year. That's what this calculates. So it's a two-step calculation. For each order ID, calculate the sum of sales, and then among the order IDs, pick out the largest one. That's what that function says. And that's what you get over here. But in order to calculate that, the engine creates an intermediate table over here. You never see this. So writing the aggr function inside here, that could sometimes be cumbersome to get everything right. But think of it like an intermediate table where you have order ID as dimension, and that's the second parameter in your aggr function, and sum of sales, the first parameter in the aggr function, as the two columns. Then you will get it right. So also that is a cube. As you notice, we have cubes everywhere. And now, a common error is this. Let's say that you want a conditional calculation. Here I've written if order date is less than some kind of breakpoint, then calculate sum of sales. Will this work? Yes.
It will calculate something.
Sorry?
It will calculate something.
It will calculate something, but maybe not what you want.
Depending on dimension.
Depending on dimension?
If you put order date or something equal granularity wise equal to
Yes.
order date,
Yes.
it will calculate.
It will calculate. So you must have a dimension so that you have the same, so that you only have one order date per row in the chart. I don't like this expression of the simple reason that now we're working with Qlik Sense, making Qlik Sense better. We want to be able to put expressions like this in the master measures, meaning that the master measures, I don't know what dimension I was going to use. So what you should do here is really ask yourself, okay, if there are several order dates, which ones do I want to use? Do I want to use the top one or the lowest one? And then put that in the equation right away. Because if you only have one order date, then it doesn't matter if you write min or max or average. All three will work and all three will give the same result. But if you want it as a master measure in Qlik Sense, then you have to think, do you want min or max? So, I think that was it. To summarize, the Qlik engine is really an on-demand logical inference and aggregation engine. And that's what we do differently from many other competitors. Questions? Or have I blown your mind so you just smoke?